So I wanted to do another experiment, but on this experiment we want to measure the moment of inertia of two objects. This right here, which I call a fat hoop right here. Remember, I for a hoop was mr squared, but that was a real thin hoop. I for a fat hoop is 1/2 times the mass of that object times the inner radius squared plus the outer radius squared. Not diameters, these are radii right here. The other item is this right here. To tell you the truth, this is also a fat hoop, but this is really fat hoop right here. So the equation is exactly the same, except the inner radius is tiny and the outer radius is way out to here. Now, just so we don't get these two confused, we're going to use the same equation, but I'm going to call this one the disk, and I'm going to call this one the hoop, just so I don't have to call one the fat hoop and one the really fat hoop. So this one I'm going to call the disk, that one's I'm going to call the hoop. So what we want to do is we want to measure the eyes using this formula first right here. Now we can measure the mass because I can put the mass right on here. So if I put the first mass on there, let's say the disk right here. Now this is the big M right here of the disk right here. So if I put that on right there, then here is 2 kilograms. Putting out there. We put another 2. Now we're up to 4 kilograms. Okay, and then I need to go even higher than that. Here's 5 kilograms. I even need to go even a little bit more than that, so we'll come over to here. So now if I start bringing this over, you notice that brings it down. So we'll come back to, it's less than 100, so we got to take the smaller scale over here and bring that over. I'll put it to the middle here first. That's too much. We'll bring it to the 40. Still too much. Bring it to the 30. Still a little bit too much. Bring it to the 20. And if I look at that, it's a little low, so we'll bring it back to the 10. And that looks pretty good right there. So this is 5.01 right here, kilograms. So this is the mass, big M, of the disk is equal to 5.01 kilograms. Okay, now we need to measure the mass of the hoop, the other one. So I'll take this one off, put this one on right here. This one looks lighter right here, so let's take off one of these and add it's more than that. It's if we stop this thing from bouncing around, it looks like it's still a little bit too heavy. So we'll take another one back to here, and we'll add way over to here. Go a little bit more. A little bit more. Right about. Looks pretty good right there. That would be 4.895. So this one is 4.895 kilograms. This would be the hoop. So we have the masses right here. We also need to get the radii of the hoop. So the best way to get the radius, I'm going to give you the diameter for the disc. I'm going to give you the outer diameter and the inner diameter. So you're going to have to cut it in half and convert it into meters, because this is going to be in centimeters. So if I look right here, this thing is 25.5, the outer diameter. So for the disc, the diameter outer is 25.5 centimeters. Again, cut that in half and move the decimal place because you want it in meters, right? I mean, sorry, you want it in meters. The diameter of the inner, right here, the diameter of the inner is 1.9 centimeters. 1.9 centimeters. Remember, you're going to cut it in half and then divide by 100. Now the hoop right here, the hoop, you can see has the same outer diameter. So diameter outer is the same. The outer is also 25.5 centimeters, but the inner diameter is going to be quite a bit bigger than the other one right there. The inner diameter is 22. Diameter of the inner is 22.0 centimeters. Again, we could get the radius, it'd be 11, and then if you convert it into meters, it'd be 0.11 right here. So just from this mass and these radiuses, you could get the eye of each object. But that doesn't mean that it is correct. I could have given you any formula up there. You could have calculated the eye. Remember, the units of eye are kilogram meter squared right here. So we need a completely independent way of measuring the eye and then see if they're equal right here. And so what I have over here is I call this the cross right here. And if we look at the picture over here, we have the cross. There's a string wrapped around this spool underneath. And then it comes over to this pulley, goes up, goes over that pulley, and back down the other side. And so you notice if we start this thing up pretty high, I'd like to start it right there, so that means it's 2 meters off the ground. This is a 2-meter stick right here. And suppose I were to put an object on, let's say the hoop on there. It just fits in there. And suppose we were to start this like this and just let it go right there. And what would happen right here? Well, I don't want it to go right now, but what would happen is, if we looked at this from an energy point of view, when we first started out, here we had some hoop or something on there. So how did we start out? Well, what started with all the energy? It was this guy, this weight that's hanging up there. So we have mgh. That's the original energy right here. Now when he got all the way down to the bottom right here, it's moving with his velocity v, all of his potential energy, some of it went into moving this, which is 1/2 mv squared. And then where did the rest of it go right here? Well, some of it went into rotating this thing right here. And so some of it went into plus 1/2 I. I of what? I of both the cross here plus the hoop. It's got both of them in there. You got the cross plus the hoop. Omega squared. And then you also have how much went into friction right here. There's friction here. You got friction on these pulleys. These pulleys have a mass. But if you look at these pulleys right here, first of all, this pulley right there, there's not much friction. You can see that right there. And we can see that the mass of this pulley is really so small compared to this mass. I used to take it into account. It really makes no difference right there. So So we'll assume that there wasn't any frictional losses on either one of those pulleys. No mass, no energy even goes into spinning the pulley because its I is so small right here. So this is, we can pretty much just assume all the energy just follows this right here. Now, what we want to get is, we'd like to get I of the hoop, because what we'd like to do is compare it with the I of the hoop when we did it this way right here, and get a percent error. So first of all, let me see. Little m is this mass right here. G we know. H we know, we're starting it from 2 meters high right here. We don't know the speed. We don't know I of the cross. We don't know I of the hoop. We don't know omega right here. But we do know there's a relationship between R and omega. We do know that V equals R omega. The only thing is, what R? How does this omega depend on the speed that this is going right here? Well, if you look at this little drum down here, the string going around the drum, the speed of the string is the same speed as the speed of this rim going around right here. So we need to get the radius of this drum right here. And so that's my little r. And so omega is equal to V over R. And we can take that omega and plug it right up into here. So now we have mgh equals 1/2 mv squared plus 1/2 I of the cross plus hoop times V squared over R squared. V squared over R squared. Okay, let's simplify this. Let's multiply by 2. So if we multiply by 2, and let's factor out the V out of these two terms, the V squared. So we end up with 2mgh equals V squared times m plus I of the cross plus hoop over R squared. Okay, now how are we going to get the speed right here? How do we get the speed down there? Well, we're going to have to get it by constant acceleration. We do know the acceleration is going to be constant because the forces here don't change on the way down. So the acceleration is constant. So what do we know? We're going to time it down, and we know the length down right here. We don't know the acceleration. The acceleration is not g. The acceleration would be g if I cut it, but it's not g. But we can at least plug in our x equals x sub naught plus v naught t plus 1/2 at squared. If I put my origin right there, called down positive, we got x, which is 2 meters. I'll just say 2 right here. Well, let's call it h. It's the same thing as h right there. So it's just h equals x sub naught 0. V naught starts from rest. So we just get 1/2 at squared. Okay, so t is the time. We'll time it down right there so we can measure that. So it looks like a, not time, but a equals 2h over t squared. 2h over t squared. Now we wanted to get the final speed, so let's plug in v equals v naught plus at. Well, v naught was 0, so we just have this times the time. Well, if you multiply this by the time, it's just 2h over t. So we've got the speed. We can measure we know the height, that's going to be 2 meters, and we know the time. So we can take that and put that right up into here. So now we have 2 mgh. I guess we only have one h. I guess this is little h right here. It's just all the same. This is all little h. H. So we've got 2 mgh equals v squared, which is this squared, 4h squared over t squared. which equals 4h squared over t squared. That's times m plus I of the cross plus hoop, all over r squared. Okay, well, we can get rid of an h here. We got an h there, we got an h there, we got a 2 there, we can get rid of a 2 there. And then let's bring the rest of this stuff over here. So we got mg t squared, that's going to come up to the top, that's the time down, divided by 2h, equals, and then we just have what's inside of here, m plus I of the cross plus hoop, all over r squared. Then let's bring the m term over here and multiply by r squared. So I of the cross plus hoop, I of the cross plus hoop is equal to, well, we're going to subtract the m over right here. So we first get mg t squared over 2h, mg t squared all over 2h minus m, and then we're going to multiply everything by little r squared. So then we're going to multiply everything by r squared. Or the last step, I of the cross plus hoop is equal to, I'll factor out what I can, mr squared, and we get gt squared all over 2h minus 1. So this looks like the formula for finding the I of whatever's spinning in terms of the little m that's dropping, the radius of the drum, gt squared over 2h right there. Okay, so now the only thing is I don't want I of the cross plus hoop. I just want I of the hoop. How do I get rid of I of the cross right here? Well, what I could do is we could come back to here, take off this, figure out what the I is of just the cross, then put this on, find out what the I of the cross plus the hoop is, and then just subtract the 2. So it looks like I of the hoop would just be I of the cross plus hoop minus I of the cross, So we need to get I of the cross first, and then I of the cross plus the hoop, and then subtract the 2. Okay. We're going to have to do that for the disk also. So this is what we're going to do. We're going to do the cross first. So we're first going to do the cross. We're going to just put the cross in there. I'm going to put for my little m, little m is this mass. You notice there's no big M over here. Big M of these masses I measured over here. We're not using it for this experiment right here. And so we have, for the cross, we're just going to use 50 grams for m. M is equal to 0.05 kilograms right here. We know what's the radius of the drum right here. If I wanted to measure this radius right here, the radius of the drum right there is, oops, got it backwards right there. This is 4.8 centimeters. So the radius is equal to sorry, that's not the radius, that's the diameter. I'm measuring I can't measure the radius, I can just measure the diameter. The diameter is equal to 4.8 centimeters. So that means the radius, don't forget you have to cut that in half, it's 2.4 centimeters right there. So there's your radius right there. So we do know the radius, right there. You got to put that in meters, so don't forget to move that over 2 decimal places. Everything should be in kilogram, meters, and seconds. Okay, we know what G is, 9.8. The time will be the time down. The H will always be the 2 meters, because that's where we're starting it from. Okay. So now what we'll do is we'll do this experiment, get the time out of here. Matter of fact, I'm not going to measure the time. You're going to measure the time right here. And so I'll just tell you when to go, and when that hits the bottom, we'll say to stop. It's got 50 grams on it right now. And I'm going to bring this thing up to here. It's right at 2 meters right there. And when I say I'm going to go 3, 2, 1, go, and that's when I'm going to pull my hand away right there. And you're going to stop it when that hits the ground right there. Okay, so 3, 2, 1, go. Okay, and I want to, just to make sure you did it well, I want to do it again right here. You could even take both measurements and average them out, but I at least want to make another one just to make sure you did it right. Okay, so now we got 3, 2, 1, go. Actually, I'm going to do it one more time, because if they were different, you want to pick the right one right here. So I just want to get that thing back on here. Okay. So run this back up. Try it one more time. Okay. And 3, 2, 1, go. Okay, so now that you have those 3 times, take the average of those 3 times. The average of those 3 times, put right into here, average. Right there. Okay, so put that number into here. Then plug it up into here, the time. G, you know the H right here, you know R, you know M, plug it all into there, and we can get just the I of the cross. Okay, and that should be in, the units of this thing should be in what? Kilogram meter squared. Make sure you're in that unit right there. Okay, and so now, what do I want to do? Now what we'll do is, we'll now put the hoop on it right here. So now we're going to do the cross plus the hoop right there. Now the mass, I want it a little bit larger because otherwise it'll take forever to get down. So I'm going to add this 200 gram to it. So now it'll be 250 grams. I got to get this back on here. So we'll put that back up there. Okay, so now the little m will now be 0.25. 0.25 kilograms. This is M. That doesn't change. The size of the drum doesn't change. The height will always stay the same. And so the only thing that's differing here is I'm changing M a lot bigger, and the time will be a lot bigger, but I'm also changing what's the I up there. So now we're going to put on the hoop right here. So now, plugging into that formula, we'll get I of the cross plus the hoop. So we'll bring this thing up to where it was, right up right up there. Okay, and then we'll time it down. 3, 2, 1, go. Okay, and so we'll time it again 3 times. Okay, about right there. 3, 2, 1, go. Okay, and then one more time. Okay. 3, 2, 1, go. Okay, so now you can average those 3 times. Get it up here a little ways. Now you can average those 3 times. Put that into here. Average. T-average. All these other numbers were the same right here. So now you can get I of the cross, because when you plug it into here, you're getting the I of whatever's spinning, and now this gives you I of the cross plus hoop. Cross plus hoop. Okay, now you have I of the cross plus hoop, you have I of the cross, subtract these two, and that'll give you the I of the hoop. I of the hoop is just I of the cross plus hoop. Minus I of the cross. Okay, so now you've got I of the hoop you got this way. You also got I of the hoop when you did it by this formula using the big M. Remember, you're not using that big M over there. You're not using these lengths either. This is a completely independent way of measuring it right there. Get a percent error between the 2 I's, between this I of that hoop and the I of the hoop that way. Okay, and now what we're going to do is we're going to put on, get I of the cross plus the disc. Cross plus the disc. Okay, we'll use the same mass that we used on this one, M equals 0.25. The only thing different is we'll take that one off, put this one on instead. Just repeat what we just did right here. The diameter is still the same, the height is still the same. We'll just get 3 new times and we'll put the average into that one right there. So we'll bring this one up. Right there, right. 3, 2, 1, go. Okay, we'll do it 2 more times. Okay, 3, 2, 1, go. And one more time. 3, 2, 1, go. Okay, so now average those 3 times, just like we did before. Average those 3 times. So now again, we'll get a T average equals. Plugging it back into this formula right here, and that'll give me the I of the cross plus the disk now right here. So now you can get I of the cross plus the disk. We want to eliminate the cross, so we'll subtract him out. We already know what he is over here. So I of just the disk is equal to I of the cross plus disk minus I of the cross. Okay, and now you get I of the disk this way. We also have I of the disk from this, using that formula, using these parameters right here. We got I of the disk. Remember, we said the fat hoop was really a disk since there was a hole in the middle of it. If you wanted to get the percent error, how do you find percent error? You subtract the 2 and divide by the one you think is more accurate. This one is probably more accurate than that one. You didn't have to time anything. So when I say a percent error, we'll just take this I of this hoop minus this one. Take the absolute value because you don't want negative error. So you take the bigger minus the smaller one and divide by this one over here. Same with the disk. You'll take the bigger minus the smaller one and divide by this one that you calculated over here. Okay, and hopefully they work out. And if they work out, then you can say, I believe in I, right here. Not you, I, right here. Okay, so now you can do that experiment.